Okay. Um, Good afternoon or good morning or hello everyone. So welcome today to the webinar. Today we talk about example selection and post-training quantization for large-scale machine learning with Professor Christopher Dessam. And this is a webinar hosted by Cornell. So my name is Bertrand. I'm co-founder at Cornell. We'll be moderating this session. But before we begin, just a quick reminding information that you can post all your questions in the chat. We'll try to keep track of it. And we'll try to either answer them during the talk or at the end, depending on what you prefer, Christopher. And now let me introduce you properly. So now, Christopher Dessam, professor at Cornell University and also team lead with one of the best experts and researcher on quantization and efficient machine learning. We'll present to you this talk. So we are very excited to have you here today with us. So now, Christopher, just please go ahead. The floor is yours. And so, yeah, we are looking forward. Thanks a lot.
Great. Thanks for the introduction. Today I'm going to be talking about a couple of relatively mature lines of work in my lab that are unified by a single mathematical idea of using a sort of linear corrector or feedback path to make better discrete decisions within machine learning systems to make those systems more efficient. And I'll start out by talking about the example selection problem. Here, this is motivated within the context of running large-scale learning. So like in stochastic gradient descent, typically your goal is to minimize some loss function. So an average over a data set of the function f evaluated at that, evaluated at a particular weight value, averaged over a data set. Typically, we do this by running SGD or mini batch SGD, where at each step you choose a example or typically a batch of examples that's a subset of the data set. You compute a gradient over that batch, which is an average over the batch, and then you use it to update your weights. And there are many things that are similar to this, like Atom, like Muon, like Adigrad. They are different in that they run a different update step, but they're still similar in that they still select a subset of data at each step. Now, how do we do this? How do we select the order in which to draw the samples? Well, the simple way that I teach in like the first level introductory machine learning class is just random sampling. So you draw each example that you use at each step independently at random from the data set. It's very easy to prove theorems about this. But it turns out this is not as good as what you could do. There are other things that perform better, both in theory and in practice. A simple heuristic is to just shuffle the data set once and then sample in that fixed order every time you pass through it. Another very common heuristic is randomly shuffling, where you basically sample each example without replacement for the data set. So you use every example once before using any example twice. And in this context, there's a nice theoretical gap in addition to like long-standing empirical observations that these shuffling-based orders are better ways of selecting data. Over the past 10 years or so, there's been theoretical advances that explain why this happens. And under standard assumptions in optimization theory, which I won't go into, but they're on the slide if you're curious, you can show that for non-complex optimization on a smooth objective, which is a reasonable proxy for deep learning, reasonable-ish, then after you run t steps of stochastic gradient descent on a data set of size n, then while for width replacement SGD, the simple thing that draws examples independently, the gradient magnitude after that is bounded by something that scales like 1 over the square root of t, the number of steps. Random shuffling scales as n to the 1/3 over t to the 2/3. So as t becomes large relative to n, as the number of steps becomes large relative to your data set size, you get acceleration from random reshuffling. And this matches what has been long observed in practice about these methods. And that's just one example of a setting in which you get a theoretical gap. There are plenty of other settings in other gaps, like strongly convex optimization, quadratic optimization. Lots of really nice theory work, especially over the past 5 years. So what we set out to ask, what started this whole line of work, is what is it about these random shuffled examples that actually make it converge faster? And the motivation is that random reshuffling, sure, I mean, it's nice to be able to prove things about it, but often, especially when you come from a machine learning systems background, you have some constraint on the order that you can use the examples in that comes from the system. So for example, if you're in a distributed setting and your data set is partitioned among workers, you're restricted in the order that you can use the examples, in that each batch needs to have the same number of examples from each worker. So it would be nice if we had some general statement about when an order of examples leads to faster convergence, so that we could apply it to whatever order of examples naturally matches the hardware and the compute structure that we have. Okay, so we did this. This is a paper from a couple of years ago, and our insight, our answer to this question is that how fast SGD converges basically depends on or scales with how fast averages of consecutive example gradients in your order converge to the full objective gradient. And I'll sort of show you what I mean by examples. So if I am drawing examples independently, if my data examples are all drawn independently, then if I ask for a particular W, for a particular weight vector, how close is an average over a run of examples that I draw of individual example gradients, how close is that average to the full batch gradient over the entire data set? And it's pretty obvious, because this is just an average of random samples, that this is going to converge at the classic Monte Carlo rate of 1 over the square root of the number of samples. However, if we look at random reshuffling, something interesting happens. For relatively small numbers of examples, of consecutive examples, it behaves like the Monte Carlo rate. But for larger numbers of examples, for larger numbers of consecutive examples that were averaged, if the examples that we're averaging contains an entire epoch, that epoch is going to contain each example in the data set once. And so all of the errors of that, those example gradients cancel each other out. Essentially, the error of that is 0. And so the error that you're left with in terms of how fast these consecutive example gradients go to the full batch gradient is basically something at the start that's like the end of some epoch, and something at the end that's the beginning of some epoch. And the magnitude of the noise from that can be at most square root of the data set size. And so the whole thing scales as the square root of n, the data set size, over m, the number of samples. And that's faster for a sufficiently large number of samples than the Monte Carlo rate. And you can actually prove that this gap sort of pushes through the convergence proof of stochastic gradient descent and gets us that accelerated rate for SG. And okay, the proof is basically based on some new assumption where we say, let's assume that the average gradient error scales as some constant c squared over the number of samples to some exponent gamma, and then you can prove a convergence rate as a function of gamma and expand this to a bunch of other theoretical classes. And basically this means that for any example order that you care about, as long as you can bound how far that example order's runs of example gradients are from the full batch gradient, you can immediately get a convergence rate. And this gave us a whole bunch of theory for free. So like you can get the classic rate for permutation SGD, the randomness shuffling rate for free. We got a faster rate than was known in the literature for the shuffle once algorithm. We got new rates for markup chain gradient descent, randomness shuffling with data echoing, many different ways of drawing gradient. Okay, so pretty nice. But can we do better? Because so far, all I've done is derived ways of getting theory and theoretical bounds for new example orders. But all the example orders that we've studied so far, that we've looked at here, they're getting either rates that are like as good as randomness shuffling or are worse. And that's consistent with what people have observed in practice. Like everything people have observed in practice has just been everything does about as well as randomness shuffling, or it does worse. A lot of things do worse. So can we do better? And here's what we did. So we just tried to design an algorithm that does better. And here's the intuition. And this is where where some of the math will come in. So the idea is we're going to take this running sum, this metric for example ordering, and we're going to use it as a sort of objective to decide what order to sample the examples in. So we're going to choose the examples to minimize this running sum. And for technical reasons, rather than looking at the L2 norm, we're going to look at the L infinity norm, because if we look at the L infinity norm, this is identical to a classic problem in combinatorial optimization called the herding problem, where if you have some vectors, x1 through xn, which all have bounded L2 norm, the problem is to find a permutation that minimizes the running sum of the differences between those vectors and their average. And what's really nice about this is that the herding problem has a known solution, and there are known algorithms that solve the herding problem and bound this L infinity norm in terms of a constant, in terms of a term that is O tilde of 1. So it's only logarithmic terms in n, the number of vectors, and d, the dimension of those vectors. And that's very promising for what we wanted to do. And so in order to figure out how to do this efficiently, though, we have to understand how people solve the herding problem. And I'm going to do a deep but quick theory dive into this to sort of try to give you intuition. The herding problem, one way to solve it, the typical way that people approach solving it is via this other popular combinatorial optimization problem called the vector balancing problem. And the vector balancing problem is a very similar problem. So you're still given a sequence of vectors that are bounded in the L2 norm, except that now instead of trying to find an order of these vectors that minimizes the running sum, we're going to try to find a sequence of signs for the vectors that bound the running sum. So equivalently, imagine you have an accumulator. At each step, you get a new vector. You have to decide whether to add the vector to the accumulator or subtract the vector from the accumulator. And your goal is to minimize the worst L infinity norm, the largest L infinity norm that you observe of your accumulator. And there's a very nice online solution to the vector balancing problem, which is just a random walk from Allweiss et al. In 2020. And this gives a really nice online solution to the vector balancing problem. So it's online in the sense that you only need to know the vectors that you've seen up until the current vector in the sequence to decide which sign to assign. You don't need to know the future. It's very nice. And this has a guaranteed bound that's big O of log of nd, and the number of vectors, d, the dimension. And a really nice thing about this algorithm is that it's really fast to run. So it's very efficient. You just maintain an accumulator. At each step, you compute the dot product of the the new vector that you get with your accumulator. There's some scalar but quite fast randomized algorithm to choose the sign based on that dot product, and then you update the vector of the accumulator based on the sign you chose. And there's a really nice reduction of vector balancing to, the very, very nice reduction of herding to vector balancing via this pair-based algorithm. So again, imagine that the vectors that we want to herd are x1 through x2n. So there's an even number of them. That's easy to assume without loss of generality. I'm going to pair those vectors up. So I pair the first vector with the second vector, the third vector with the fourth vector. For each pair, I compute the difference. I then run the vector balancing algorithm on that difference, producing a sequence of signs. And then the trick is that I now update my order, my example order, to produce a new order where for each pair, if that pair was assigned a positive sign, I assign the first element of the pair to go to the start of the next, of like the new order, the new permutation, and the second example of the pair to go to the end of the new permutation. And if the sign was negative, I do the opposite. I assign the first example of the pair to the end and the second example of the pair to the beginning. And you can show that if you do this, that the L infinity norm of this herding worst case value over the whole permutation is bounded from above by 1/2 times the the L infinity norm of the previous permutation. There should be an L infinity norm here, and I don't know what happened to it. The L infinity norm of the previous permutation plus 1/2 times the vector balancing bound. And so what you get at the end of this is your herding metric, the worst case L infinity running error of the permutation, is less than or equal to 1/2 times the worst case running error of the permutation that you started with, plus this vector balancing bound, which recall is O of log of ND. And so this means that we can just repeat this over and over again to get arbitrarily close to the vector balancing bound. Because at every step, your sort of herding metric, how good your permutation is improving by a factor of 1/2, and then you add this vector balancing in. And this naturally gives us a way of doing better example order selection in SGD by simply running one step of this herding by a vector balancing algorithm as we're doing each epoch of SGD. So, concretely, we start with some random permutation. Every time we get 2 example gradients, we subtract them. We send their difference to the online vector balancing algorithm. We then use the sign to decide where to send those 2 examples for the next epoch's example order. And then in the next epoch, we have a permutation that's better in the terms of this metric. And what's nice is that under sort of somewhat standard assumptions, the only assumption that's a little bit suspicious is this cross norm L smoothness term that needs to relate the L2 norm to the L infinity norm. You get this better convergence rate that says that you scale as big O tilde of t to the minus 2/3 times problem parameters, which is better than random reshuffling because it drops this n to the 1/3 term that you had in the theoretical bound of random reshuffling. And theoretically, then there's this comparison where our algorithm gradient balancing will tend to do well when the number of examples is large relative to how much you lose by having to sort of move from the standard L2 Lipschitz smoothness constant to this slightly weird L infinity including Lipschitz constant that we have in the theory. Although it turns out that this can be improved, and there's some nice follow-up work that improved that and basically dropped the need to have this annoying L infinity constant. But rather than go into that, I'm going to show some empirical results. So here's some results on convex optimization. This is just logistic regression on MNIST. You can see that GRAB, the pink line, is better at training loss and is also better in terms of validation accuracy than the baselines, including randomness shuffling. Greedy here is just a line for a very expensive non-Einstein algorithm that solves the herding problem via another more classical approach. And this also applies to deep learning, which is really cool. So this is, training in LSTM, fine-tuning BERT Tiny, and again, the magenta curve just seems to do really, really well. What's really cool about this, although we didn't prove it ourselves, but this is actually optimal. So in 2023, there was a result that gave matching lower bounds to the upper bounds achieved by our algorithm. So not only is GRAB better than randomness shuffling, it's actually optimal among all permutation methods. No permutation method could do better, at least in terms of the asymptotic rate, than GRAB. Okay, so there is this suspicious dimension dependence where we added this cross-norm LL smoothness, and this theoretical thing has been actually relatively recently resolved. So this great paper by Annabelle Carroll out of Lester Mackey's group has basically shown that via a low-rank kernel thinning algorithm, you can practically replace that kind of annoying cross-norm dependence with a much more tractable data-dependent measure that just in practice typically translates to almost no overhead at all. And you can basically eliminate this and make the algorithm work just as well and have really nice theoretical guarantees. So this is like a really cool improvement. I guess I should have advanced my slide because it has the... Anyway, this is just the slide version of what I just said. And they have some really nice results too that matches our best algorithm in practice and has better theoretical guarantees. So their improvement is this green series here. We can also make this distributed. So we did a modification that allows us to run in distributed hardware, works really well. And okay, great. So better than randomness shuffling, that was what everyone was doing. Should everyone use this? Well, okay, not so fast. There's two caveats, right? One caveat is that the algorithm does have overhead, and the overhead is the overhead for this accumulation buffer. So the additional memory cost, you should think about it as kind of similar to the cost of a buffer in Momentum or an Atom, which has to be the size of the model. And you may not want to pay that cost. That's one limitation. And the other limitation is that you only get a better rate when you actually run multiple epochs. The asymptotic improvement is in the number of steps large relative to the data set size regime. And in a lot of modern settings, particularly pre-training settings, you only run one epoch. And so you shouldn't expect to get that much of an improvement from this algorithm in the only one epoch case. In fact, in the only one epoch case, GRAB is identical to randomness shuffling because it doesn't make any changes until the second epoch. There's some reason to believe that even if we're running one epoch, there could be some amount of data repetition, at least conceptual data repetition, allowing gradient balancing to work. Just as some cursory reasons to believe that might exist, we know also from some of our work that there are some texts that are memorized by large language models. And so probably there is some amount of repetition of information that would cause those texts to be memorized. And so it would be interesting to ask whether we can somehow leverage that informational repetition, even if it's not like the same training example actually being repeated verbatim, if there's some way we can leverage that to get better example orders. But that's an ongoing subject of research. Great. So lots of potential improvement from example orders. And you can use it on GitHub. It's available if you're curious to use Graph. Next, I want to talk about the second topic very briefly, because I'm running quite low on time. It's post-training quantization, compression. So the idea is you have a big model, you want to make it smaller. And the classical rounding approach that people used is that they choose a scale factor for their grid, and then you round each of your weights to the closest number in the grid. So like you round it to the nearest integer, and then you check your accuracy and you hope that it wasn't too bad. A better approach is adaptive rounding, which has been covered in a lot of papers. I just call it adaptive rounding because that's like the first paper that gave it a name and proposed describing it. The idea is that you use some sketch of the Hessian of the loss functions. You approximate your loss function with a quadratic, and then you try to round your weights in a way that minimizes this quadratic. And there are many ways that you can do this, heuristically or non-heuristically. Our line of work looks at this a little bit theoretically, and the question that we start with is, imagine what for this objective, for this quadratic loss function, what would existing methods get? What would like the basic methods get? One of the most basic quantization methods is stochastic rounding. Like it's just slightly more complicated than nearest neighbor rounding. Here you round either up or down so that the expected value of the output after quantization is the same as the input. And here it's pretty easy to see that your proxy error, this quadratic for randomized rounding to the integers, is just 1/4 times the trace of the Hessian matrix, the quadratic Hessian sketch that you were trying to minimize. So the goal theoretically is to do better than this. And here we're going to take the same sort of approach that we did in the example selection thing. So for herding and for herding by vector balancing, we had a accumulator that we used to provide some linear feedback to decide how to order. And here we're going to do the same thing. We're going to imagine that at each step when we round, we're going to round based not on just the value of the weight that we want to round, but based on that with some linear function of the previous quantization error that we add to the current thing that we're rounding in order to try to correct for any error. And here, I'm going to imagine that the weights for this linear feedback, the Aij, are so far arbitrary. We're going to set them later. We can write this in a matrix form A, where A is strictly lower triangular, as W hat is equal to round of W plus A times W minus W hat. And via a matrix decomposition, if we let L transpose DL be the LDL decomposition of H, so it decomposes H into a unit lower triangular matrix times a diagonal matrix times the same unit lower triangular matrix transposed. Then if we set this correction factor to be L minus I, so the lower triangular component, strictly lower triangular component of L, then one thing that we notice is that the proxy loss, the difference in W transpose times H times the difference in W, can be factored as this difference in W times I plus A transpose times D times I plus A times the difference in W. And if we round in this way, it's pretty easy to show that each entry of I plus A times W hat minus W is bounded by one, just by some calculus, just by some like algebra. And so because this is a vector whose entries are all bounded by 1/2 in magnitude times the diagonal matrix times that same vector, the error must be less than or equal to 1/4 times the trace of that diagonal matrix. And you can show theoretically that this choice of A is optimal, and this also is equivalent in terms of the result that is actually computed to GPTQ, which was a really popular and still is quite popular pre-existing algorithm. So then the question is, can we do better than classical rounding with this? And well, the obvious answer is that we will do better in cases where the trace of D is small relative to the trace of H. Is the trace of D always small relative to the trace of H? Well, not necessarily. If H, for example, is a diagonal matrix, then the decomposition is just going to have D equals H, because L, the lower triangular matrix, is just going to be I, the identity matrix. And so you get no improvement. But it turns out that this is an outlier case. And in most cases, the trace of D is small relative to the trace of H. And in particular, for average matrices, for like a random matrix, the trace of the diagonal part of the LDL decomposition is going to be small relative to the trace of H. And in fact, it scales roughly like 1 over D times the trace of H to the 1/2 squared. And you can make this notion of averageness rigorous using a concept from linear algebra called incoherence. And so what we're going to say is we're going to assume that all of the unit eigenvectors of H have this property that the maximum magnitude of an entry is less than, for some constant mu over the square root of D. Then you're able to show this acceleration. You're able to show that the trace of D is less than or equal to mu squared over D times the trace of H to the 1/2 squared, which is going to be small relative to the trace of H when the matrix H has a rapidly decaying spectrum and when D is large compared to mu. But okay, this is all fine, but H is just something that comes from our Hessian sketch of the model. We can't really change it. We can't ensure that it's incoherent. And in fact, if you look at the real ones that you observe, they're not incoherent because they have outliers, and outlier features correspond to large components that make the eigenvectors of the Hessian be very well aligned with the coordinate axes. So this is a problem, but we can just make H incoherent, force it to be incoherent, by multiplying it by a random orthogonal matrix. And so if we do something like this, we choose some fast random orthogonal transform, we replace our linear layer with apply the transform, invert the transform, apply the linear layer, and then apply a second random transform and invert it. Then we fuse the internal transforms together by doing a matrix multiply of the weights, and then we quantize those weights. Then what we get is a fast to multiply linear layer proxy that has much better incoherence properties and gives us a nice end-to-end guarantee on what the proxy loss is going to be. Obviously, to make this run efficiently, we have to have that multiplication by a random orthogonal matrix be fast. That's pretty easy. We just use a randomized Hadamard transform, which takes time O of D log D, and we show empirically and theoretically is basically just as good as having a fully random orthogonal matrix. And so our method, it was called QuIP, in quantization with incoherence processing, and it did better than most of the prior works at the time. And we have a bunch of improvements. So we improved it by adding vector quantization. That's QuIP sharp. It basically groups of 8 weights together and quantizes them based on the E8 lattice, which is a really fun geometric structure. It further improves it. We got even better using trellis quantization. At this point, we're essentially recapitulating like the last 70 years of information theory to basically improve our quantization. Basically, all of these questions result or like reduce in some level to the question of how best to transmit information over a noisy channel. And it's in some sense just the dual of that problem, where here we're trying to represent a bunch of Gaussians in terms of bits with minimum error. And their information theory, they were doing the opposite, trying to represent bits as real valued signals that might be corrupted with random errors, but the mathematics is the same. And by using these like trellis codes, which are really, really nice information theoretic compression scheme, we're able to do even better. Trellis codes are actually pretty cool. They're equivalent in some sense to just using a pseudo-random number generator to generate the weights. So here, what you do during decompression is you have your compressed weights be a sequence of bits at b bits per weight. You have some pseudo-random number generator function that maps an L-bit code into something that looks like a unit Gaussian, a random unit Gaussian. And then you basically decode the kth weight as a pseudo-random number generator, or your pseudo-random number generator, applied to a chunk of L bits that slides through the sequence of bits as you run decode. And so it's actually super fast and really efficient to implement. And you can do it really efficiently for compression too, although there are some theoretical limitations. And this it turns out, way better than the previous work and is able to run really efficiently on real GPUs. We have a final improvement that rather than trying to get a better method of compression, we try to get a better Hessian sketch. And this also improves things quite a bit. And I just also want to shout out the work of some of my students who developed a method for training large language models with MXFP4 that also, to some extent, uses some of the same techniques, including this randomized Hadamard transfer. So yeah, to get some takeaways, understanding that, the maths of linear feedback can give us some big wins in compression. We're able to, by getting a good theoretical handle on what's going on, design better algorithms here. And this idea of linear feedback has a wide range of applications. So thank you for listening to my talk. And I also work on a whole bunch of other things, including extracting training data from large language models, manifold learning, hyperdimensional computing, machine learning hardware, digital agriculture, and Markov chain Monte Carlo. So I'd be happy to take any questions now.
Thanks a lot, Christopher. I think that was amazing. Very clear overview, of course, making both your training more efficient with training some selection, and also functions more efficient. I have some questions, but not some questions in the chat as well. So maybe I can ask the first one from Sean. So is the main advantage of QuIP its speed and efficiency, or does it also deliver better accuracy than GPTQ or other quantization algorithms?
So I've gone back to the slide, and granted, this is just at the time that we produced QuIP. This is just the time that we produced QuIP. And so the comparison was against GPTQ. OPTQ is the same method as GPTQ. It's just a different name for it. And you can kind of see that at 2 bits, comparing this orange curve to this blue curve, QuIP is better. And it's a little bit harder to see, but comparing these two kind of pink-like curves, you can also see that that QuIP is better at 3 bits too. So both 2 bits and 3 bits, it's delivering better accuracy. The trade-off is that it does, there is some extra compute that you have to effectively hide within the system by running things efficiently. Pull back to this. Yeah. So here, you're replacing a high bit linear layer with some randomized operation, like a randomized Hadamard transform, and then a 2-bit operation and another randomized Hadamard transform. So there is some overhead relative to GPTQ. So if you just compared it to GPTQ, QuIP has better accuracy, but has some efficiency trade-offs. And those efficiency trade-offs are on some hardware negligible, and on other hardware they might not be negligible. It really depends on how efficiently you can hide these randomized Hadamard transforms.
Right here. I have maybe a follow-up question. Another question is, it looks like the improvement you shown are really focused on codebook quantization, either vector quantization or not, right? So I was wondering if there is any other takeaways that you can apply to linear quantization with activation quantization as well, or that's something that is hard to translate.
I didn't hear the last thing you said. I heard you say linear quantization with, and then
I don't know. Linear quantization is also quantizing the activations so that we can do also the instructions and linear instructions in low bits.
Oh yeah, good question. So basically all the theory just applies to this weight quantization regime because all the stuff that we're doing is too costly to do at inference time. Because it involves taking a matrix decomposition of some large Hessian. However, you can just use the randomized Hadamard transform and then quantize the weights and the activations, and it will just work. And in particular here, in this training LLMs with MXFP4 work, this work does do activation quantization as well. So it's not just, or I mean, it's quantizing it's quantizing the error signals in the backward pass to MDFP4, MXFP, to MXFP4. So there is some sense in which things beyond the weights are being quantized. And the randomized Hadamard transform helps with that too, simply because it removes outliers that would otherwise be problematic. So, most of our theory is about adaptive routing that takes the Hessian into account, but the randomized Hadamard transform just helps regardless. And of course, it comes at a cost of doing that extra operation.
Excellent narrative, thanks. We have another question. So from Louis, so super cool subjects. Where the idea of linear error feedback is coming from, the one you presented on GPTQ's ideas. Why not imagine an error correction term that is not linear? Any ideas if some concepts can emerge from it?
Yeah, so in terms of where it came from, what I thinking about it, it's basically this algorithm, the online vector balancing algorithm. Because I always used to think that you could do a lot with error feedback, but that the error feedback needed to be sophisticated or complicated or somehow learned. And what kind of surprised me about the online vector balancing algorithm is that linear feedback, some linear difference, actually suffice to get the optimal convergence rate there. And that started to make me think, well, if linear feedback works well here, where else could it work well? And it turns out that even in some of these more complicated regimes where it seems like something more sophisticated is needed, you can do a lot with linear feedback. And the nice thing about linear feedback is that you often can set the weights, your feedback weights, in a way that is optimal by solving some mathematical optimization problem to minimize a loss. Like that's what we basically did. Where is it? Here, right? If you want to figure out what the best way of random linear feedback is, you don't actually need that much in the way of like clever insight beyond writing the problem like this. You can write once you write the problem like this and you figure out what the expected error is, that expected error is literally just a quadratic function in A that depends on the Hessian H. And then this particular choice of the weights A, the feedback weights A, just drops out of solving that optimization problem mathematically. So, and that the ability to do that is really enabled by the fact that the error feedback is linear and results in mathematical problems that are simple enough that you can kind of solve them by hand. So I think that using linear feedback is in some ways motivated by me wanting to solve problems that are tractable to solve. And then maybe in the future, I hope in the future, we'll be able to find feedback that is better than linear. But we can already get so much from the linear case. And in the grad setting, we actually proved that it was optimal, that linear suffices to be optimal.
Do you see what could be non-linear feedback that could be useful for like a quantization? So since it's already optimal for a graph.
Yeah, I think for quantization, some sort of feedback scheme that takes overflow into account might be better. So currently, right, QuIP using this linear feedback scheme. The linear feedback scheme is not designed for cases where you can have overflow. And so the feedback basically assumes that you'll get a bounded error no matter how large your differences are in between your current vector and your rounded vector, even if those differences are huge. Now, in practice, this doesn't cause too much of a problem. It doesn't overflow that much. But I think it would be interesting to look into that. And additionally, this type of rounding works really naturally in cases where the thing that you're rounding to has evenly spaced quantization points. So you're rounding to a lattice or you're rounding to the integers. For floating point quantization, it does still work pretty well, but it doesn't exactly match the theoretical setting. And so maybe some sort of nonlinear quantization that takes floating point variance in the error or differences in the error in terms of the magnitude of the thing that you're rounding, maybe that could also do better. But I'm just speculating.
Okay, that was super interesting to get the insights from. What could be an interesting way to improve it. There is a question from Andrei. Thank you for two interesting talks. I work in constraint optimization for neural networks. So quantization is new but interesting topic to. As I understand, QuIP relies on the Hessian matrix of the weights, satisfying the incoherence property. Potentially, we could enforce the property on the model using constraints in training. Think of it as linearization with better qualities. Do you think it could be worth it?
Oh, so this is a good question. And so the answer is yes, although I wouldn't use the word enforce so much as like allow or enable. So the thing is, right, what you want for it to be incoherent is for the matrix to essentially have a random set of singular vectors or eigenvectors, all of your matrices. And neural networks are actually like this almost naturally. So for many neural network architectures, if you were to just rotate your embedding vector by a random rotation, that completely preserves the function that's being computed. Like you basically randomly rotate all the embedding vectors, randomly rotate all of the weight matrices in the appropriate way. It's all the same. And so intuitively, it in some sense ought to be the case that the matrices and the activations are invariant to rotation and distribution already, because they're part of the model family that's invariant to rotation and distribution, and they were initialized in a way that's invariant to rotation and distribution. What gets in the way of this is Adam. Adam has is an optimizer that has this second momentum buffer that is not invariant to rotations. And so this is part of what causes the outliers. If you choose an optimizer like stochastic gradient descent that doesn't have any, that is rotationally invariant, you can ensure this property that the weight matrices tend to be incoherent, and they'll just stay incoherent the whole time because there's no particular reason why they should be coherent with the coordinate axes. Obviously, to make this work, you would have to drop things like the scales of the layer norm, which are also element-wise. There's a lot more hand-waving to be done. It should be possible But there's a question of whether doing that gives up very much during training and will give up accuracy down the road. And so I think this is an interesting open-ish question about how different optimizers that result in networks that have fewer outliers might do better in terms of quantization and might be able to trade that off against accuracy. And ideally, we can find an optimizer that produces incoherent models, that doesn't have outliers, but that still gets basically the same scaling law accuracy curves that Adam currently gets.
Thanks a lot. There is another question from Afonso. So thanks for the insightful presentation. Could the QuIP be scaled or combined to quantization-aware training?
Yes and no. So can it be used at each step to do quantization? Probably not. It's too expensive. You can't do it at each step of the optimizer. Can it be done as like a pre-processing step before doing quantization-aware training? Absolutely. And then basically all of our more recent papers, what they do is after applying QuIP, so after applying the Hadamard transform and doing the quantization and producing the quantized model, we then run a few epochs of quantization-aware training after that to try to recover some of the error that we lost. And so it can absolutely be combined in that way.
What would be your key papers that you will go for to do this? That you worked on?
I think that the QTIP paper does it. And we certainly do it in YAQA, YAQA.
Okay.
Yeah.
So great. I have some question about Grab as well. Sir, Grab, I guess you decide kind of for the ordering of the examples like to train on. Did you notice that there is also this notion of maybe you should train first on difficult examples and then on easy examples, for example? Did you even
notice this kind of, oh yeah, I should try to have a I used to have a slide on life
and then I cut it. Curriculum learning is that type of thing. And it's weird that it's completely at odds with the intuition behind Grab. So the intuition behind Grab is that you should have every run of examples be as close to distributed according to the whole data set as possible. And curriculum learning says the opposite. They should be different at the start of training and then harder at the end. I don't know. I don't actually know of any theory around, certainly an optimization theory around curriculum learning. And we didn't really try combining the two, and it's not obvious how we would combine the two.
Okay. Maybe a follow-up question is like, did you see that the epoch after epoch, like the order, like the selected first examples that should be applied at a specific epoch change kind of? So or how does it change? Like what?
Oh yeah, so the model converges to good orders. And in the sense that what is a good order is not actually like there's no sense, it seems, of there being a generically good order for neural network training because the optima that you go to are subtly different. But for convex optimization, if you run it to the end and then pick the order that you have at the last epoch, and then consider recapitulating, rerunning the training process using just that order over and over again, it will converge just as fast as Grab, if not faster. So it is finally a good order. However, the order does not converge because the way the algorithm works is that at each step, you're pairing up consecutive examples in the order and then sending the first of the pair to the beginning and the second to the end, or vice versa. So at every epoch, the order is really substantially changing. Any thing that was right next to each other in the previous epoch are on opposite ends of the new epoch. So even though they're converging in the sense that they're getting better, it's not like it's converging to a single particular best permutation.
Very interesting. Okay, makes a lot of sense. I have a last question, I think, from Ashish. So where can we find code, examples, resources?
Oh, basically any one of these papers. So if you just like search the title of the paper, they'll be on our GitHub. And usually, sometimes they're in the lab GitHub. Usually, the Git repository is owned by the lead student, who's the first author of the paper. But the vast majority of these papers have just code on GitHub that can be used to reproduce the experiments.
Amazing. And thanks a lot. I think we are approaching to the end of this webinar. So first, again, a huge thanks to you, Christopher Ardosa. I think that was like really good session covering like a lot of different parts of the efficiency. So really interesting. So before wrapping up, I wanted also to say, don't forget to check out also what we do and at Puna in terms of open source and models. And feel free also to follow us. And we for sure gonna have some next webinar, regarding like state of the art research as today. And so thanks a lot. So hope to see you again like soon. Thanks a lot again.
Take care.